Welcome. This is lecture number 28. In this lecture, we are going to talk about DC analysis using equivalent circuit model. So, the concept here we are trying to derive the DC equivalent circuit of ideal as well as the practical DC-DC converters. Then we need to find the steady state voltage gain and also we need to carry out loss analysis. We also need to find out what are the practical limits on voltage gains as well as the efficiency, okay, and then few simulation case study and verification. So, before we start, we need to consider start with the point, and in the previous class we derived the small signal model from large signal model, I will say, which consists of both DC as well as AC, both using state space averaging as well as the circuit averaging technique in the past two lectures. So, we want to continue some of the results that we have shown in the previous lecture, where we have obtained some equivalent circuit using either circuit averaging technique or we also can use average switch model. Okay. So, if you take a conventional buck converter, then we can write down its realistic model just considering the parasitic drop resistance of the MOSFET and for the diode the resistance of the diode as well as the diode drop and also the DCR of the inductor and ESR of the capacitor. Then we also found the equivalent circuit of this conventional buck converter in the previous lecture, and this can be obtained by if we want to apply the equivalent switch model, that means the average switch model, then we need to make this switch ideal switch. That means all the parasitic has to be taken right side, that we have taken. You say this Vd which is there, it actually came here with 1 minus D because this is activated during the off time. This resistance is activated during the on time and this resistance is activated during off time. That is why you can see this effective resistance is combination of D into R1 plus 1 minus D into RD. So, I can separate out this term and I can make this switch ideal. Then we can easily apply the equivalent switch average switch model, and then we can derive the equivalent circuit model using average switch model. So, in this model we already have discussed in the previous class that how to obtain the per turn term, how to deal with the DC term, and this represents the duty ratio of the buck converter using a DC transformer. Here the Rx can be shown to be the inductor of the resistance plus D into R1, that is the on state resistance, and 1 minus D into RD. So, now if R1 and RD are same, let us for example, if we take a synchronous buck converter where the on state resistance of the high side switch and the low side switch, if we take nearly equal, then this Rx will be simply RL plus R1 because D plus 1 minus D will be 1. And here we can drop this diode drop in a synchronous DC-DC converter, that also you can do. So, this is a more generic model which can be used to derive the model for the synchronous buck converter, where Vx can be obtained, this Vx, that is RD minus R1. So, if these two are identical, this term will get 0, become 0, okay, and if these two are identical, then this term will also become R1 which is equal to RD. So, it is RL plus R1. The DC equivalent circuit, in order to obtain DC equivalent circuit from this model, it is very easy because we know the DC model. For the inductor, the impedance is SL, for the capacitor it is 1 by Cs, we know. So, if limit S tends to 0, that means we are operating at very low frequency, this will eventually become 0, and if we put limit S tends to 0, so this will become infinity. That means this circuit should be open and this circuit should be shorted, and this is exactly what is the DC equivalent circuit. And that is the beauty of this technique, that we can very easily obtain the equivalent DC circuit simply by shorting the inductor and opening the capacitor. Next, all the part of terms should be set to 0, because if you take this particular term, for example, it consists of two terms. One is input, which is a DC term, plus V in. So, if this is our source, okay, this can be divided into two parts. That means it is basically the sum of two sources. One is our capital V in and another is our V in hat. Okay. So, that means it is just the sum of two by using superposition. Now, under DC equivalent circuit, all the perturbed terms is set to 0. So, for a voltage source, it will be shorted, for current source, it will be open. So, we did it, that means we shorted the perturbed term, so is set to 0. So, it is simply V in. We open this part because D perturbed tilde D is 0. So, the current source will be open. We shorted this term, so but this is a constant term, so it is there. Okay. Then this term is also a perturbed term, this will be shorted because it is a voltage source, and this Rx is already there, it is already a resistive term. Inductor is shorted and capacitor is not there, so this resistance has no meaning because this is not part of the circuit and the load resistance. So, we obtain the DC equivalent circuit from the equivalent circuit model. Next, once we have the DC equivalent circuit, now we want to analyze. What can we analyze? We need to find out the voltage gain. So, now this is a simplified form of the DC equivalent circuit. In fact, if you draw this circuit can be redrawn where Rx is given as, because I can take this source to this side by suitably taking into account the transformer gain, voltage gain. This will be our DC equivalent term here, it is D into V in, okay, and there is another source, okay, this is 1 minus D or D dash into Vd, diode drop. Then we have some Rx resistance and this is our load resistance R, and this is our V0 plus minus. Now, how to obtain what is the effective voltage here? This will be dV in minus 1 minus D into or D dash into Vd. Okay, so the simplified circuit, I have shown you that this particular term you can further simplify as this is the net voltage, which is dV in minus D dash Vd. This is my voltage and I have Rx here and R here. Then I can obtain this voltage, that means this voltage can be obtained by here. So, this is the term I told you, the subtraction D into V in, this consists of these two terms, effective term, and then this is Rx, which is nothing but this term, and the voltage here will be R divided by the total resistance R plus Rx. That means our V0 will be D into V in minus D dash into Vd, this is a term, multiply the resistive divider R plus Rx, R plus Rx. Then what is the voltage gain? We know the voltage gain of any DC-DC converter, voltage gain is the output voltage by input voltage, right. So, this is exactly is the output voltage by input voltage, and if you take V in out of, I mean if you take V0 out of this particular term, what you will get? First of all, you take D into V in at the beginning, right. So, that means I am taking, that means here from here to here V0 by V0 equal to D into V in multiplied by 1 minus d dash Vd by dV in this term into, now if I divide R below, so it will be 1 plus this divided by R. So that means 1 divided by 1 plus Rx by R, simply this term. And if you take this thing, so V0 by V in, which is my kV, is equal to D times 1 minus d dash Vd by dV in this whole thing 1 by 1 plus Rx by R. So, this is exactly this. So, this is my correction factor, because in an ideal buck converter, for ideal case it is equal to D for ideal case. That means when there is no diode drop, there is no parasitic resistance, so it is simply the deuteration. The voltage gain is simply the deuteration. But in practical case, this is something like a correction factor or correction term. This should be multiplied to get the suitable voltage. Okay. Now, what will be the efficiency? So, efficiency will be output power by input power. What is the output power? So, here the average current will be IN by D. So, what is IN? IN, we can find IN for a buck converter is D times IL average, which is nothing but the load current, right. So, you know this, and this is nothing but the D times load current, because it is going to the load. For a continuous conduction mode buck converter, the average inductor current is same as the average load current, because the capacitor average current is 0. Next, so this is fine. What about this? If you replace with this, you will get V0 by V in into I0 by d I0, and if you cancel it, you will get V0 d into V in, or it is simply 1 by d into kV. Okay, so it is written here. Okay, so I can erase this particular part. So, V0 by V in, that means this is my efficiency. This is my efficiency. So, this term we have already obtained. Now, you substitute the voltage gain. This is the voltage gain. If you substitute the voltage gain already has 1 by D, because we know from the voltage gain in the previous slide we saw D into the correction term, right, correction term, and this is my correction term, That means my efficiency is 1 by D times D into correction terms, and this is cancelled. So, this efficiency is simply the correction term. So, your efficiency under ideal condition, you can set Vd to be 0, and if you set this all this drop to be 0. So, if you set Vd to be 0, then this will be only 1, and if you take all the parasitic drop to be 0, this time will be 1. So, efficiency will be 100%. That means we should multiply with 100 in terms of percent. If we want in terms of percent, then we can multiply 100 to get percent. But in practice, it is much lower due to the diode drop, due to this parasitic resistance. Now, if we take a synchronous buck converter where we are not considering a diode, that means in synchronous buck converter, if we draw the actual circuit, so this is like this, and we are assuming the on resistance to be identical for both the cases, identical, For simplicity, this is my switch, this is my switch bar, this is my inductor, then this is my capacitor ESR, this is my L, C, and this is my load resistor. Now the DC equivalent circuit will be what that we saw. So this is my Vin. So DC equivalent circuit will be my capital Vin, capital Vin, and this resistance is my R equivalent, and this is my resistance, and this is my voltage. Sorry, there is a transformer term because actually, yeah, so here there is a factor, a DC factor which is 1:D, and this side you have Vin. That means if you transform, it will be D times Vin R equivalent by R, and this is my capital V0. Okay. So that means my voltage gain, which is V0 by Vin. So if you write V0, what you will get? You will get D into Vin into R by R plus R equivalent, right? Okay, which is nothing but D times V in to 1 by 1 plus R equivalent by R. Okay, and this is exactly what we are showing, because we are taking V0 by Vin. If you take this term will get cancelled. So we are taking the left side. So D times this R equivalent is, so this is the on state resistance. So here it is the on state resistance of the on state resistance. Okay. That means my practical duty ratio is D is the ideal duty ratio multiplied by this correction factor. This is again the correction factor, the correction term. And so what we can expect, the practical output voltage will be input voltage into practical duty ratio, because suppose I want to achieve 12 volt input to 1 volt output. For ideal case, I tend to set 1 by 12 is the duty ratio. But practically for ideal converter, you will get, I'll show you 1 volt output, but practically you will never get when particularly the load current changes. Okay, and the efficiency of this converter can be simply the correction factor. So that means you can see the efficiency, because this is nothing but 1 by 1 plus R equivalent by R. That means if the load current increases, this term will decrease, and if this term decreases, this term will increase, and as a result efficiency decrease. Okay. So that means we can predict that if for R decreases, that means higher load current implies the efficiency also decreases. That means for higher load current efficiency decreases, and that is why we have discussed earlier that if we consider a load current plot, that means if you have resistance, if you plot load current under continuous conduction mode, it will decrease, because this is due to the conduction loss, and which can be modeled by this equivalent resistance. But this is a DC term, we have not incorporated the ripple current, only the DC term. Okay, so for accurate loss we need to go for RMS current calculation and all, but this is just the DC equivalent. Okay. Now I want to show a simulation case study. Here I am talking about an ideal synchronous buck converter and a practical synchronous buck converter, where the blue trace is the one which is the ideal one, and it is the one. and the red one is the practical one, which is number 2. This is number 2. What is my operating condition? Here I made a load change here. So, I am showing you all the details. So, load resistance changes from 1 ohm to 0.05 ohm. So, this side our R was 1 ohm, okay, and this side onward R become 0.05 ohm. For the time being, do not consider this transient effect, because that we are going to discuss in the subsequent lecture. But for the time being, let us consider the steady state. Let us take, I am talking about this particular window, okay, this particular window. Here also I am talking about this particular window where we can think of steady state, this particular window. What we will find? Firstly, our objective to achieve 1 volt output for 12 volt input, and that is why I said the ideal duty should be 1 by 12. But you will find for ideal condition the output is actually coming to 1 average sense, and our for 0.05 ampere load resistance. So, what will be the load current? So, it should be I0 should be my V0 by R. So, if the V0 is 1 volt and I0 is 0.0 ohm, so it will be 20 ampere. So, my average inductor current is 20 ampere, that is shown here. But for practical converter, it is much below. This is not 20 ampere, it is less than 20 ampere, and the output average voltage is much lower. How can we model? That means we did already DC analysis. So, now I am showing the zoom version of the condition where the resistance was 1 ohm. Under this condition, the average inductor current seems to be more or less same, very close, okay, but the average output voltage there is a slight deviation. So, can we analytically show what is the value? We know the load resistance is 1 ohm, and in our converter setting we took the R equivalent to be 10 milli, R equivalent to be 10 milli ohm, because 5 milli ohm is the DCR and 5 milli ohm is the on state resistance. So, it is totally 10 milli ohm. So, what is my practical duty ratio? It is the ideal duty ratio multiplied by this correction factor, right? We know about this correction factor, correction term. Then what is my practical average voltage? Practical average current, for ideal average current we know it is D times V in by R, or basically D times V in is my V0 by R, which is my average inductor current, and it is 1 ampere. But for practical inductor current, it is dP, that is a practical duty ratio input voltage, and which is 0.99, and if you see the average of the red, it is almost the 0.99, because the midpoint is the 0.9, which is more or less close to our predicted value, because this is a midpoint, so which is in between 1 and 0.98, and average inductor current is almost, so sorry, average inductor current it is almost 0.99, sorry, 99. So, they are more or less same, like only maybe 10 milliampere difference. But now, under the same condition, we want to see the output voltage average. Again, the duty ratio calculation is given. Ideal output voltage is ideal duty ratio in the input voltage, that is 1 volt, and that is coming exactly, average value exactly coming to 1 volt. This is my 1 volt. But my practical output voltage can be calculated by V in multiplied by my practical duty ratio, which is this, because this is my correction term, and it is 0.99, which is also consistent because it is also the midpoint, okay. So, it is also consistent. Now, can we make the same thing for the load resistance when it is 0.05? Under 0.05, my R is 1, R equivalent is this. sorry, here R should be 0.05 ohm. So, I can find out my D practical using this formula, this correction term multiplied by ideal duty ratio. So, my ideal inductor current is 20 ampere, which is the average value is same as this. My practical current is 16.7, which is coming to this average value. Average value is 16.7, which is consistent with our analysis. Now, coming to the practical output voltage. So, if we calculate, again it should be 0.05. Now, my ideal in output voltage is 1 volt, which is like this, but the practical it comes to be 0.833. That means, if we take this average, it is coming to be 0.0833 volt. That means, we can predict so we can reasonably predict this output average voltage, practical output average voltage from our DC equivalent circuit, and that we have shown and matched with the simulation result. The next task, we can do it for a boost converter. Again, we start with the circuit, we can add all the non-ideality, then we can obtain the equivalent circuit that we have already derived in the previous class. So, I am not going to repeat. Then, in order to get the DC equivalent circuit, we need to short the inductor and open the capacitor, and that is the circuit is here, and then we need to make suitable transformation. We can, in this case, we can transform this into this side, and then we can, this is a simplified circuit, or here in this case we have transformed right to left, left to right, we can do any side. Then we can find the voltage gain. In ideal boost converter, the voltage gain is V in by, output voltage is V in by 1 minus D, but in practical there is a diode drop into another term which is due to the resistance drop of the parasitic, that we also found. So, the expression can be obtained for this circuit, and if you do the efficiency calculation, then the efficiency will not be much less than 100% due to this factor. Okay. Now, another interesting point, if you take the voltage gain of the boost, so if you take a synchronous boost converter where the diode drop is 0, and if we take the on state resistance, because we are talking about two switches, high side and low side, and let us say both switches have a same on state resistance. So, if we take that, then again we can write the efficiency here can be, there is a correction factor and this is a voltage gain. This is my ideal voltage gain of a ideal boost converter, but this is the correction factor. And what is R equivalent here? R equivalent not only RL R1, but there is also an ESR term comes, but this is very small, it is too small. So, it can be approximated as RL plus R1, where this is my on state resistance, on state resistance. Okay. Now, I want to show you an interesting point. Here, if you see the expression, the kV, for ideal converter, we know kV is 1 minus D. This is for the ideal, which means if I increase duty ratio, my voltage gain will increase and I can achieve any output voltage of an ideal boost converter. If we take, let us say 3.3 volt is the input, then I can achieve even 300 volt in an ideal boost converter by suitably setting the duty ratio, but practically it is never possible. Why? Because in practical case it is 1 by 1 minus D, it is there, but there is a strong dependency of duty ratio in this term, and when duty ratio increases, this term becomes smaller and this term becomes quite large, and your voltage gain will start dropping, and this shows a nonlinear characteristic of the voltage gain. And if you plot the voltage gain for this synchronous boost converter, For the ideal one, which is here I am showing RL by R, or basically here you can think of RL, or which is R equivalent. If you take R equivalent by R, which we are ignoring for the time being the ESR effect, this R equivalent captures both on state resistance as well as the inductor resistance. Okay. So, here this R equivalent, so I can also consider R1. Okay. So, this R equivalent, which is RL plus R1, if this is 0, that means if we do not consider any parasitic drop, you see the voltage gain can be increased like anything. But practically when this term comes into picture, then this maximum voltage gain is achievable at this point, and this maximum point shift quite drastically when this resistance ratio become larger and larger, and this is true when R equivalent by R, this ratio can increase if for a fixed value of R equivalent, if the load resistance decreases. That means as the load current increases, the load resistance decreases, the ratio increases, and then your voltage gain falls. Similarly, for the same load current, if this equivalent resistance increases, then also voltage gain falls. So, in a boost converter, the practical voltage gain is limited by this parasitic drop, which is primarily due to the drop of the resistance, the drop of the on state resistance for a synchronous boost converter. For a ordinary, like a conventional boost converter, it will also be a function of diode drop. Okay. So, efficiency of the boost converter also will get significantly affected with this parasitic drop, and if you tend to achieve higher gain, you will lose the efficiency like anything, and nobody will because we want to achieve efficiency more than 90%, so which is achievable for a lower duty ratio operation. So, you have to be very careful about the selection of the voltage gain, and there are multiple research papers which is actually proposed to increase the voltage gain with higher efficiency, so where the ordinary boost converter cannot achieve. So, practical voltage gain in a boost converter, DCR of the inductor limit the maximum possible voltage gain. As duty ratio close to 1, voltage gain becomes 0, so it start falling, and a low duty ratio converter offer higher efficiency. So, for high step up operation, there are many possibilities. One can consider multiple cascaded stage, but that also increases number of component, device complexity. One can go for isolated converter, and recently there is a there is a research thrust to consider the flying capacitor boost converter multi-level, where the number of flying cap, if you keep on adding, the voltage gain can be increased with some reasonably high efficiency. So, in a conventional boost converter, efficiency drastically decreases as the duty ratio increases, that we have seen. Same thing can be extended for a buck boost converter. We have already derived the buck boost converter. So, this is a realistic model. We have derived the equivalent circuit for a buck boost converter, where we need to achieve, or we need to get the DC equivalent circuit, because this circuit I have already shown in the previous class. Here what we need to do? We need to replace inductor by shorting it, and capacitor has to be open. And if you do that, then the DC equivalent circuit can be obtained, and from this equivalent circuit we need to find out what is my voltage gain. That means my voltage gain, that is my first point. So, if we try to find the simplified circuit, so you can map back all these stages to this side, and you see there is a reverse dot convention which takes into account the polarity. That means, if you take from right to left, the polarity has to be reversed along with the step down ratio. Okay. So, if we write down all this DC equivalent circuit, then we can find out the voltage gain, and here for an ideal buck boost converter, the voltage gain is simply D by 1 minus D. Okay, for if you take kV, which is V0 by V in, this is equal to minus d by 1 minus d in case of an ideal case. And this is an inverting buck boost because there is a negative sign and we know about this. But in a practical buck boost converter, your voltage gain also get affected because of this diode drop and because also this parasitic resistance along with the duty ratio. And we can obtain all this expression and we can carry out the same technique which we have done for the synchronous buck converter. We can simulate this buck boost converter as well as boost converter, and I will suggest that you verify the average value of the inductor current and the output voltage for different load condition. Using this analytical DC equivalent circuit, you can predict what will be the practical voltage when you set a fixed duty ratio and vary the load current. You can predict using this analytical formula. You can carry out the same thing by simulating. We can check whether can we predict it or not. And also the efficiency of the converter, we can write the output power by input power and we can write down all the expression of the input current in terms of output current, and we can find out the efficiency, and it can be shown that efficiency is much lower than 100% when the diode drop is high as well as when the load current is high because of the parasitic drop. So, for a synchronous buck boost converter, again we can write down that this is my ideal voltage gain and this is my correction factor, and the efficiency will be simply the correction factor that we have discussed. So, this is same thing like for buck boost and buck boost for the synchronous configuration, the efficiency is simply the correction factor, that is the beauty. So, that if the correction factor becomes smaller, the efficiency will fall, and if you multiply with 100, then we can write in terms of percentage. So, with this we want to summarize that we discuss about DC equivalent circuit of ideal and practical DC-DC converters. We discuss about the practical limit of the voltage gain. Though we can achieve lower voltage gain for a buck converter with this drop, but for a boost converter we cannot increase the voltage gain beyond a certain value because of this parasitic drop, and this voltage limit will be imposed by the on-state resistance of the DCR and the resistance of the on-state resistance of the MOSFET plus the DCR of the inductor. But even if we choose a smaller on-state resistance on the DCR by using a costly inductor, still this voltage gain will be limited when the load current increases. Okay? So, that means there are practical limits, and it is not recommended to use boost converter as like a ordinary boost converter for a high voltage gain application. And we have shown few simulation case study for a synchronous buck converter, and the same thing can be carried out for boost as well as non-inverting buck boost, and we can verify. So, with this I want to finish this lecture. Thank you very much.